Welcome to this presentation on weather-based irrigation scheduling. I'm Alan Andales, Professor of Irrigation and Water Science in the Department of Soil and Crop Sciences, and my co-author is Andrew Jones, Senior Research Scientist in Cooperative Institute for Research in the Atmosphere. We are both at Colorado State University. When we use weather data in irrigation scheduling, we incorporate the weather data into the daily water balance of the soil profile. Now, the daily water balance is tracked in terms of the current deficit, or what is called the net irrigation water requirement. This deficit is based or referenced from field capacity. If the soil water content is at field capacity, where the soil is holding as much water as it can against gravity, then there is no deficit. And as the water content of the soil drops below field capacity, then that deficit builds up. And on a daily basis, the deficit, or that net irrigation water requirement, can be calculated from the previous day's deficit and adding all the terms that make the deficit grow. The major subtraction of water from that soil profile is the crop evapotranspiration, or water uptake by the crop, and that adds to the deficit. That's why it has a positive sign. And other losses such as surface runoff and deep percolation also make the deficit bigger. Those terms that are negative are additions of water into the soil profile and reduce the deficit. These are precipitation, irrigation, and capillary rise that is possible from a shallow water table, if there is such presence of a water table. And the weather data is incorporated in the calculation of ETC. Of course, precipitation is measured by the rain gauge, and these two terms really incorporate the weather. The estimation of crop evapotranspiration is done using this equation. The reference crop ET is estimated from weather data and represents the potential amount of evapotranspiration from an actively growing crop. And there are two types of references in general use. First is the alfalfa reference, and the other is the grass reference, ET. For agronomic crops, we typically use the tall or alfalfa reference. And the red text in this definition represents the assumptions that go into the calculation of this reference ET. This reference ET is then multiplied by a crop coefficient, Kc, which scales down the level of ET to the actual level of the crop that's being estimated. And then another factor is the soil water stress factor, which represents soil water stress based on the moisture content of the soil profile. Ks of 0 represents maximum stress, while a Ks of 1 represents no stress. What's important to note is that crop evapotranspiration is driven by the energy supply at the surface of the crop. And that is represented here in this diagram as the net radiation. Net radiation is calculated by summing up all the terms or components of shortwave radiation, RS, mainly coming from the sun, and long wave radiation coming from terrestrial bodies that have temperature, And once you sum those up, you get the net radiation at the crop surface. Now the net radiation, not all of it is used in evapotranspiration because some of it is lost through ground heat flux, which is represented here by G. In addition to net radiation, the three other weather terms that we need to consider are humidity, which is represented here in this diagram as E, or vapor pressure, air temperature, T, and wind speed, U sub Z. Wind speed measured at a certain height above the ground at level Z. Now, when we measure weather, the sensors are placed at a measurement height represented by this dashed line above the canopy that's being tracked. And these are typical profiles of vapor pressure, air temperature, and wind speed that occur above a canopy. As you go up in height from the surface, where the humidity is almost at saturation, or 100% relative humidity, that's represented as ES, saturation vapor pressure. And as you go up to the measurement height, you get an actual vapor pressure of the air. And similarly, the temperature at the surface is relatively warmer because of the radiation. And as you go up into the air, you get an actual air temperature or ambient air temperature. The wind speed increases as you go up into the air and up to the measurement height of the wind speed. This photo here shows a good source of weather data for evapotranspiration. This is a typical weather station having sensors for all those four components that were mentioned, plus also a precipitation or rain gauge to track the rainfall amount. This is a good source of weather data since the station is surrounded by well-watered clipped grass, which is the recommended surrounding around a weather station. On the other hand, this photo shows a bad source of weather data because it is surrounded by dry land. And dry land would overestimate the temperature and underestimate the vapor pressure or the humidity. And this would lead to overestimation of the reference evapotranspiration. So when we use weather data for irrigation scheduling, we should be using weather data representative of irrigated conditions. In Colorado, we have what is called the Colorado Agricultural Meteorological Network, or COAGMET. This is showing a map around the state of Colorado. There's right now around 85 or so weather stations across the state, concentrated around irrigation or irrigated regions of the state. And these can provide those four major weather variables that we mentioned, plus precipitation from the rain gauges. Now, as I mentioned, the reference ET is calculated using a standard equation, and we use the American Society of Civil Engineers, ASCE, Penman-Monteith ET equation, which incorporates those four major variables: net radiation. Ground heat flux is subtracted from net radiation because not all of that net radiation is available for evapotranspiration. We have air temperature, and we have wind speed measured at 2 meters height. That's why it has a subscript of 2. And then we have humidity represented by vapor pressure, which is represented by E. Now the Ks, the water stress coefficient, is determined from the water content of the soil. And here at the top of this graphic is the range of water content from field capacity, which is the maximum available water in the soil, all the way down to wilting point. This is where the plant can no longer extract water. Every crop has what is called a management allowed depletion, which is the portion of this available water where the crop starts experiencing water stress. And as you can see, the red line represents the Ks value when the moisture content is between field capacity and DMAD, management allowed depletion. There is no water stress, so the Ks is 1. And as soon as the water content, or this depth of water, goes below management allowed depletion, then there is a linearly increasing stress represented by a decreasing Ks. So once the moisture content hits wilting point, the Ks is 0, and therefore there will be no evapotranspiration. Again, the three terms in the ETC calculation, and this is the equation that represents that red line in that previous slide. Now, this is an example of how a crop coefficient is derived. Crop coefficient curves are derived experimentally. The reference ET is measured using weather sensors to calculate the reference ET using the ASCE Penman-Monteith equation. The actual ETC is measured by an instrument called a Lysimeter. Essentially, it's a box that sits on top of a weighing scale, and that box has soil with an actively growing crop. And so this Lysimeter can track the evapotranspiration, the actual evapotranspiration of the crop. And the KC, every day, the ETC from the Lysimeter and the reference ET from the weather data can be taken as a ratio, and this ratio represents the crop coefficient. These are photos of an actual Lysimeter installed in Rocky Ford in southeast Colorado, where there is an outer tank that houses all the underground instrumentation. This is the weighing scale, essentially a truck scale that holds the tank, the Lysimeter tank that's full of soil, and everything is buried underground and only the Lysimeter surface is visible. And this is all planted to crops so that the surface of the Lysimeter represents an actual field, and the surrounding of the Lysimeter is maintained or managed in the same manner as the crop inside the Lysimeter. This is showing a crop of corn growing on the Lysimeter. And following that procedure that I showed, we can get a crop coefficient curve throughout the growing season from day 0 of planting all the way to harvest. And the blue points here on this curve show actual crop coefficient points. And then if we fit a smooth line or a smooth curve through these points, we can get an average crop coefficient that can be used to calculate daily crop ET values. Those crop ET values can be used in the water balance equation, and those can go into irrigation schedulers. Now for the Ogallala water project, we had 3 irrigation scheduling tools that were simultaneously being improved or developed. The first one is WISE at Colorado State University. CanSched which is being developed at Kansas State University, and DIEM, Dashboard for Irrigation Efficiency Management, developed at Texas A&M. And these all use the water balance method and weather data. As an example, this is an output of the WISE irrigation scheduler on a web browser, where the blue curve is showing the up and down movement of the soil water deficit, and the red curve shown here is the management allowed depletion, or the threshold for irrigation. And irrigations are recommended when the blue curve, the deficit, goes below or approaches the management allowed depletion. Of course, the weather sensors keep track of the ET that goes into the water balance, and then precipitation is also tracked by the rain gauge. This is an example of the ETC estimated by WISE. Showing here at the top graph is 3 irrigation treatments, 3 sets of irrigation treatments. So the gray dots show a drought treatment where there was no irrigation, and the blue dots show the irrigated treatment, which also exhibited the highest levels of crop ET. And correspondingly, the lower graph shows the KS, the water stress coefficients associated with each of those points at the top of the curve, where the gray KS curve shows the lowest values of KS, and that's why it resulted in the most stress, and correspondingly the lowest values of ET, crop ET. This is an example graph from CanSCED, very similar to WISE. It shows a soil water curve and the management allowed depletion, which is the threshold for irrigation, the permanent wilting point, and then field capacity at the top over here. And they also show the precipitation and irrigations as bars showing up on specific dates. Here's the website for CanSCED. Now for each of those irrigation scheduling tools, there is an opportunity to incorporate weather forecasts. For example, here in WISE, we do account for a 5-day weather forecast only based on temperature to estimate future ET, and we estimate the water balance 5 days ahead. So shown here in circle. Now, great improvement to use of weather forecasts would be to also incorporate what are called quantitative precipitation forecasts, shown in this graph here. This is an example of the NOAA Weather Prediction Center quantitative precipitation forecast from June 2017 through 2018 for precipitation amount of 1/2 inch, 0.5 inch. As you can see, this graph shows what's called a threat score for different months of the year. And when you go 1 day ahead into the forecast, which is represented by the red curve, you have a higher confidence of these predictions of 1/2 inch of rainfall. There's a higher threat score because of the higher confidence for a 1-day weather prediction. As you go further into the future, you can see on day 3, the threat scores are lower because there is less confidence that that amount of rainfall will be achieved. And so there is room for improvement in terms of using rainfall weather forecast. But as we move forward, as the models, the weather forecast models improve, those confidences should also improve. In terms of using or estimating future irrigation water requirements, DIEM, the irrigation scheduler developed at Texas A&M, uses a slightly different approach. It uses weather data, actual weather data until the current day of the year, which is here, shown here in the graphic. An example is August 1 is the current date. And beyond that date, it just uses historical weather data and plugs it into the water balance model. And this provides the model weather data all the way through the end, through harvest, just based on historical weather. Usually a 10-year or a 30-year average of weather could be plugged into the water balance model to estimate this. But as the season progresses, the the actual weather data coming from the weather station can be slowly incorporated, and the calculations of the water balance continue to improve. That's the presentation on use of weather data for irrigation scheduling, and I'd like to acknowledge all the team members that were involved specifically in developing and testing WISE, and also the funding agencies and companies that also funded development of these irrigation scheduling tools. Thank you.